Hello everyone, welcome back to Basic Electronics classes. I am Lavanya Vaishnavi. Today I am going to take Module 4, which is BJT applications, feedback amplifiers and oscillators. So this is in the session 5, I am going to discuss about feedback amplifiers. Today I am going to cover the topics like topologies of feedbacks and gain and bandwidth of feedback amplifier, gain stability with feedback amplifier. So there are different topologies in feedback amplifiers. So they depending upon the usage, depending upon the requirement, we will select what type of topology we can use for the given circuit. The first one is voltage series feedback. Next is voltage shunt feedback, current series feedback and current shunt feedback. These are the 4 topologies of feedback amplifiers. So if I take voltage in series with your input, so if you just remember, we had V in as input and this was given to a amplifier and we used to get V0. In between that we had a feedback path with gain beta and this was giving here to a mixer which is VF. If this VF is a voltage factor and it is in series with your input, then it is voltage series feedback circuit. If VF is voltage circuit and it is in parallel with your input voltage, then it is voltage shunt feedback circuit. If the feedback is a current factor, if it is not a voltage, if it is current, then it is current series or current shunt based on whether the current is in series or the current is given to shunt. Okay. So shunt in the sense parallel. Okay. So voltage series feedback amplifiers feedback circuit, voltage shunt feedback circuit, current series feedback circuits and current shunt feedback circuits. These are the 4 different topologies that exist using topology that exists in feedback networks. So we have only one topology to study, which is voltage series feedback amplifier. So in this voltage series feedback amplifier, so I'll first describe what are all the elements we are having. Vin is the input voltage, V0 is the output voltage, Vf is the feedback voltage, beta is the feedback factor of the loop, and look at this amplifier. This is the amplifier having an open loop gain of A. Vi is the input to the amplifier and Zi is the input impedance of the amplifier. Z0 is the output impedance of the amplifier. Zif is the input impedance of the total circuit and ZOF is the output impedance of the total circuit. RL is the load resistance connected of the output side. Okay. So this is voltage series feedback. Why it is called voltage series feedback? Because so if I look only this part of the circuit, I can write this circuit like this. See, look at this. So you have Vin here, right? This is Vin. To this Vin, you have a voltage source connected which is minus plus Vf, right? So these two are in series, right? If you look at this properly, these two are in series. So this is in series with Vf is in series with Vin. Therefore, this is voltage series feedback. Voltage series feedback. Now, suppose the circuit is like this. So here you have a short circuit path. This point is connected here and this point is connected here. Now look at this circuit. So you have a short circuit path. This is connected here and this point is connected like this. Now look at this circuit. So Vin is like this, right? And to this you have parallelly Vf connected like this. Okay. So it means that these two are shunt, parallel to each other. This is voltage shunt feedback. So luckily you don't have that topic to study here. We have only the voltage series. So we will study only this voltage series feedback amplifier. Okay. So this is voltage series feedback. That is why, because Vin and Vf are in series. So we call it as voltage series feedback. From the figure, we can say that Vf is a feedback signal. Beta is the feedback factor. Therefore, Vf can be written as beta into V naught. Beta into V naught. It is amplified by the factor beta and it is multiplied to V naught. Vf is equal to beta into V naught. A is the open loop gain. So I told you gain of basic amplifier. Only the gain of this amplifier, which is open loop gain. And you can also call it as gain without feedback. So without feedback, what is the gain? So it is V naught by Vi. V naught by Vi. What is the input you are giving here? It is Vi, right? So it is V naught by Vi. And this is negative feedback. What is the value of Vi here? Vi is defined as, so Vi is defined as Vin minus Vf. Vin minus Vf. Okay. So the next one is, so in the same circuit, the value of AF. What is AF? AF is closed loop gain. It is a closed loop gain. Gain of the overall system, which includes amplifier and also it includes feedback network. So the gain with the amplifier and with feedback network will give you the closed loop gain, which is V naught by Vin. So V naught, I can define it as A into Vin, right? So here from this equation I can write, so from this equation I can write V naught is equal to A into Vi. So the same thing I have written here. V naught is equal to A into Vi. Vi is equal to Vin minus Vf. So I told you like Vi is Vin minus Vf. But what is the value of Vf? It is beta into V naught. So Vin is equal to, so Vin is equal to, Vin, I'll write it as Vin only. But what is Vf? It is beta into V naught. Beta into V naught. Okay, this is what we have written here. In the next step, so V naught is equal to A into Vi. A into Vi. But what is the value of Vi? Vi is Vin minus beta V naught, right? So V naught is equal to A into Vin minus beta V naught. Okay. So I have taken the same expression. If I multiply this becomes A into Vin. So this one A into beta V naught. Okay. So I have two terms common here. Here I have V naught. Here also I have V naught. So let me push this to the left hand side. So if I push it and take V naught common here, I'll remain with 1 plus A into beta equal to A into Vn. So if I rearrange the terms, I'll be getting it as V naught divided by Vin is equal to A divided by 1 plus A into beta. What is V naught divided by Vn? Which is AF. That is the complete gain, the total gain of the circuit. So closed loop circuit, AF is equal to V naught by Vn. So please rectify this. V naught by Vn equal to A by 1 plus A into beta. This is how you calculate the gain of overall system. Thus the negative feedback reduces the gain by a factor of 1 plus A into beta. If we make use of negative feedback, the complete output voltage will be reduced by a factor of 1 plus A into beta. Whereas if you look at the equation of positive feedback, we get here minus. So 1 by 1 minus A beta is definitely greater. Like it will give or it increases the value of your output. Therefore, we can say that negative feedback will reduces the gain of the given system. Okay, now coming to let us talk about the impedance of the system. So input impedance, that is the opposition force offered. Now coming to the impedance of the system. What is impedance? This is the opposition offered to the flow of charges. Now what is input impedance here? Zi is the input impedance of amplifier. Zif is the input impedance with the feedback, which is equal to Zi into 1 plus beta. Output impedance Z0 will be the output impedance of amplifier. ZOF, that is Z0 with feedback, is the output impedance of the total system, which is equal to Z0 divided by 1 plus A into beta. So this is the impedance of the next slide is gain and bandwidth of feedback amplifier. So I'll take two gains here. One is the gain without feedback and the other one is gain with feedback. Because I am taking negative feedback here, the gain with feedback reduces here. Okay. So now I'll assume that this is the point of gain, which is A0. So to understand the concept, I'll take A0 is equal to 5. Just one assumption where gain is equal to 5. And so I need a reference point to mark the frequency values F2 and F1. For that I'll take A0 by root 2. A0 by root 2. Why is this root 2? Because I'll be getting 3 decibels of difference when I take it in log scale. Okay. So or just understand A0 by root 2, which is equal to 5 by root 2. So what is this 5 by root 2? It is nothing but 0.707 of A0, which is 0.707 of 5, whose value will be approximately 3.535. So I'll take 3.53. Now I'll mark the point which is 3.53 and take the frequency values here. What is the frequency value? This is F1. What is the frequency value here? It is F2. Okay. So now this is F1 and F2. So F1 and F2 are between these frequencies, the bandwidth, we say this is the bandwidth. It means that between these two frequencies, we get maximum gain. We get maximum gain. So if I want to operate any circuit, if I want to operate the circuit, I should operate between these two frequencies. I should operate between these two frequencies. If I go beyond F2 or if I go below F1, my gain will not be maximum. The gain of the circuit will not be maximum. That is what bandwidth defines. That is what bandwidth defines. Now I told you we have two gains taken here. One is A0, which is open loop gain. The other one is AOF, which is gain with feedback. Gain with feedback. Now let me assume AOF is equal to 1. Then 0.707 of AOF is 0.707. We are taking two different points again, which is F2F and F1F. So difference between these 2 points is bandwidth with feedback. Okay. This is the bandwidth without feedback. So look at this, bandwidth with feedback and bandwidth without feedback. So with the feedback, value is more compared to without feedback value, right? BWF is greater than BW, right? If you can see, the range is increased. This is how we can tell that the range of frequency, operating frequency, is being increased. Now let us come to the bandwidth. So bandwidth is equal to F2 minus F1. So this frequency, the highest frequency minus lowest frequency. We know that F1 is very, very small than F2. Therefore, bandwidth is directly equal to F2. Approximately, you can equate it to F2. Next, the same thing, bandwidth with feedback F2F minus F1F. F1F is smaller than F2F. Therefore, bandwidth with feedback is equal to F2F, that is second operating range. So this is what gain and bandwidth is. So you can see that feedback, with feedback, the gain is reduced. With feedback, the bandwidth is increased. Okay. The gain reduces, the bandwidth increases when we make use of negative feedback. Okay. Gain stability with feedback. So what happens to the stability? What happens to the stability? And what happens to the stability of the gain when you have a negative feedback? That we will see it here. So we know that AF is equal to A divided by 1 plus A into beta. This is what we have derived in the previous previous slides. So let us differentiate both the sides with respect to A. So we will be getting it as DAF divided by dA is equal to differentiation with respect to dA of A into 1 plus A beta. So we have A in numerator and in denominator also. So it should be treated as d by dA of U by V. Now according to that expression, if I differentiate it, I'll be getting it as, so first I'll differentiate with respect to A. So it becomes, I'll take this 1 plus A beta aside, into 1 it becomes, right, minus, so this I have differentiated numerator. Now I'll differentiate denominator. So numerator I'll keep it aside, A into differentiation of 1 by 1 plus A beta, which is nothing but differentiation of 1 is 0 plus A beta is beta divided by 1 plus A into beta whole square, right? So next step, I'll multiply those terms. You will be getting it as 1 by 1 plus A into beta minus A into beta divided by 1 plus A beta whole square. So if I take LCM here, I'll be getting it as LCM and multiply it. I'll be getting it as 1 plus A beta minus A divided by 1 plus A into beta whole square. Okay. So that is what it is written here. Yes. In the next step, I left beta here. So A into beta. So A beta get cancelled and I'll be remaining with, so here A beta and A beta I am getting cancelled. I am remaining with 1 divided by 1 plus A into beta whole square. Okay. So in the next step, what I'll do, I'll split this term. Okay. So if I split that term, it becomes 1 divided by 1 plus A into beta into 1 divided by 1 plus A into beta. I'll multiply and divide by A both the sides. Now both the sides in the right hand side. So here it becomes, instead of 1, I'll multiply A. Here it becomes A. Okay. So if I look at this expression, this complete term is same. So I can write it as differentiation of AF with respect to A is equal to AF into 1 divided by A into 1 plus A into beta. Okay. So now let us cross multiply these things. So the same thing, you got it here, right? Now if I cross multiply these things, that is So if I cross multiply these things, it becomes, so look at this. Now let me cross multiply these things. It becomes DAF divided by AF is equal to, this I'll send to the right hand side, dA divided by A into 1 by 1 plus A into beta. 1 by 1 plus A into beta. Now the same expression is written here. Yes. Now if the value of A into beta is very much greater than 1, very much greater than 1. Say for example, so A beta, if it is equal to 1 kilo, okay, 1 kilo. So 1 kilo plus 1 is approximately equal to 1 kilo, right? So this complete term will be equal to A into beta. Therefore 1 divided by A into beta. Now what is this expression? D of AF by AF, that is change in AF. Differentiation of AF is change in AF with respect to AF. This is change in A with respect to A. So it is multiplied with a factor of 1 by A beta. Because A beta is a greater number, 1 by A beta will be smaller number. It means that this factor will reduce. Instead, we can tell that this shows that the relative change in dA by A in the basic amplifier gain is reduced by a factor A beta. So this gain is reduced by a factor A beta, and the change in differentiation of AF with respect to AF will also reduce. Overall, the gain change is also reduced. So the change in the gain is reduced when you take a feedback amplifier with negative feedback. This is what the equation represents. Okay. So this is all about feedback amplifiers. Thank you everyone. Thank you for watching this video. If you have any doubts, you can write me back to my email ID. Please like this video, share with your friends and subscribe to this channel. Thank you.